Thanks everyone for attending. I am Leandro from Linaro. I work with the toolchain team, mostly with LLVM. And today I'm going to talk about benchmarking in the cloud. So I'd like to start by first defining a benchmark as a program that is designed to assess the performance of a given system. And for this, commonly used metric is the execution time that a given program takes to run. And the problem with benchmark is that sometimes it is hard to get consistent results between different runs. There are many reasons for this. One of them is that modern CPUs are quite complex. So, for instance, they have cache memories that can make a program run faster if the data they need are already in cache. Some CPUs also can increase or decrease their operating frequency depending on things like CPU usage and temperature. And another thing that is present in some CPUs is that some CPUs have a non-uniform memory access, which means that some regions of memory can have an access time that is faster than other regions of memory. And all of this introduces possible variations in the measured times. And there's also the operating system that can cause interference in the benchmark program that is running. For instance, they usually cache recently used files, and they must also service hardware interrupts. So, for example, when a new network packet arrives, the operating system needs to handle it and forward it to the appropriate process. And also if other background processes are running at the same time as the benchmark, they can also consume CPU and RAM, which is also going to interfere with the measured time of the benchmark. And when we try to run benchmarks in the cloud, besides all the previous challenges, we have new ones. So one of them is virtualization, that it's usually used in cloud environments, and they have associated overheads. Another important part is that performance counters are not always available on virtual machines. Although these don't impact the measured time, performance counters are essential to diagnosing performance issues. And also in the cloud, a benchmark is usually running in an environment with shared resources. So our cloud instance may be running together with processes from other users, and this can cause interference. Even when the other processes are assigned different cores, there still can be some interference between them. And some examples are CPU cache pollution. That is basically when a cache line from the running program is replaced with data from another program. And there's also memory bandwidth contention that may happen if several processes are trying to access memory at the same time. And so given all these challenges, is it possible to run benchmarks and get consistent results using the cloud? Let's try to find the answer. To try to answer the previous question, what I did was to run SPEC benchmark in a few different cloud instances. And this slide shows some characteristics of these instances that are common to all of them. So all processors tested use the ARch64 architecture. As far as I know, none of them use dynamic frequency scaling, so they should run always at the same frequency. I have used at least 2 gigabytes of RAM per core, which should be enough for SPEC. And these processors also have only one NUMA node, so access to all memory is constant. It has a constant time. And these cores have private level 1 and level 2 cache and shared level 3 cache. And for storage, all of them use SSD or SSD-based disks to try to avoid any interference from storage. And the test setup, I have used SPEC CPU 2017. It's a benchmark suite designed to stress CPU, memory, and the compiler. I have used 3 iterations, and mainly to try to measure the variance between each iteration. For spec rate, it was run using only 1 copy. So this means that each benchmark is run on a single core. And for spec speed runs, all CPU cores were used. These tests were performed on Ubuntu 24.04 and inside a Docker container that was mainly used to make it easy to reproduce the test environment across different cloud instances. The compiler used was LLVM 21.0, and the used flags were O3 and LTO. Before I move to the result charts, I just want to make a few quick notes about them. The instance times displayed in the charts are, and the standard deviations are actually the geometric mean of the time of all benchmarks. So for instance, the spec inch time for a given instance is the geometric mean of the times of each integer benchmark. And for the mean times and standard deviations, they were calculated over the instance times. Okay, so let's start with the Graviton4 results. In this chart, we have the cloud instances organized by the number of virtual CPUs in the horizontal axis. The vertical axis has the time in seconds. And for each instance, there is the time for the integer benchmarks and for the floating point ones. And what you can notice here is that the times vary quite a bit if we consider different instances. If we look at the mean, the standard deviation is quite high. But on each individual instance, the standard deviation is not very high, but it is significant still. And another interesting point to notice is the instance with 96 vCPUs. It has the best time overall, and its standard deviation is very low. This instance actually is a bit different from the others. I'll talk about it more briefly. And here we have the worst cases that are the benchmarks, the individual benchmarks that had the greatest standard deviation. We can see that in some cases, for a single benchmark in the same instance, it was over 5%. And if we consider all instances, the variation can be as high as 20%. And well, also notice the maximum standard deviation for the 96 vCPUs instance is near 0. So this instance, the one with 96 vCPUs, is actually a bare metal dedicated instance, which means that it runs on physical hardware that is not shared with other AWS users. So there are no other processes running there at the same time. and which means there's no interference in this case. It also runs directly on the hardware, so there's no hypervisor, and which avoids the virtualization overhead. And for this particular test, it was also run inside outside Docker container to also avoid any potential overheads from Docker. Okay, this is the result for SPEC speed, also on Graviton4. The previous chart was for SPEC rate. Please note that the scale in this case is a bit smaller, which makes it harder to visualize the standard deviation. But the values for the standard deviations are similar to those of SPEC rate. And in this case, there is no mean, because for SPEC speed, all CPU cores are used, so it's hard to relate one instance with another. And another thing that we can notice here in this chart is that the floating point tests benefit more from having multiple threads available. For the worst cases, they were somewhat similar, usually not very high, but for the instance with 32 vCPUs, for the integer benchmarks, it was over 10%. And here are the results for Graviton3. They are, in regards to variation, they are similar to those of Graviton4, in which the standard deviation is not very high on the same instance, but if we compare the different instances, then it's quite high. And for the worst cases, they stayed around 2% of standard deviation in the same instance, and across multiple instances, it was over 6%. And this is the results for the Cobalt 100 from Microsoft Azure. The results are similar to the previous ones, especially with regards to the variation. And the worst cases are more or less similar, around 1-2%. There was one instance that it was over 5%, and across all instances, the biggest variation was 10%. Now for Google Axion, the results are different. We can see that the measured times are very similar one to another, even when we consider different instances, and the standard deviation is very low. Even when we look at the worst cases, if we consider only the benchmarks running in the same instance, it's less than 0.5%. And considering benchmarks across all instances, it's less than 2%, which is a good result in terms of variation. It's only after the result of AWS dedicated instances. A possible reason for this could be the Google Titanium technology that is used for these instances, because it offloads network and I/O processing, and also uses hardware acceleration for the virtualization services. Another possible reason could be that I got really lucky with these instances and no one else was using these machines. And in this chart, we have a comparison of the performance of each cloud instance tested. In terms of performance, we can see that Google Cloud had the best result. And next, there is Graviton4 for the floating point benchmarks. For the integer benchmarks, Cobalt 100 performed slightly better than Graviton 4. And in last place is Graviton3, that is an older CPU. And in terms of variation, Google Cloud also had the smallest amount of variation, followed by Graviton 4. And for Cobalt 100 and Graviton 3, we had higher values for the standard deviation. Notice that in this chart, I have considered the times only of the instances with 8 and 32 vCPUs. So the bare metal instance and the other sizes of Graviton 4 were not included in this comparison. A few notes of the previous chart. Please note that this is only an approximate estimate because it was based in only a few runs with only a few instance types, and all of them are subject to random interference from other tenants that could be running at the same time as the benchmark. So if these tests are run again, the results may be different because of these factors. A brief overview of the costs. Considering the instances with 32 vCPUs and 2 gigabytes of RAM, the cheapest one was Graviton 3, and also it's the one that had the slowest times. After that, there's the Graviton 4 and Cobalt 100 that have similar prices. And the most expensive instance was Google Axion, but it was also the fastest. Just notice that in this case, this is the cost for the standard instance that has 4 gigabytes per core, because in my tests, the one with 2 gigabytes was not available. For the bare metal dedicated instance, the cost was much higher, about 3 times of the other instances. But in this case, we get 96 vCPUs and exclusive access to the hardware. An important consideration that I want to make is that performance counters worked only on Graviton 3 and Graviton 4. And this is an important thing to consider. Because they are very important when trying to analyze and debug performance issues. And what we could see in terms of variation in the previous graphs is that it's usually low if we consider the same instance, but are quite high when we consider the times across multiple instances. And they can also be high if we consider only an individual benchmark. And I think I hadn't mentioned in the previous chart, but if we go back to the Graviton 4 chart, we can see that more vCPUs don't guarantee better performance or less variation. And also, we could notice that some workloads are more sensitive than others, because in the previous charts, we saw that integer benchmarks usually had standard deviations that were higher than those of the floating point benchmarks. So based on these tests, considering only the tested instances, the best options for getting consistent results on the cloud would be first, AWS bare metal instances, with the main disadvantage being that they are more expensive. And next would be Google Axion instances, with the main disadvantage being that performance counters didn't work on them. I would also like to mention that both Azure and Google Cloud have offerings that are similar to AWS dedicated instances, but I simply haven't explored those. For future work, it would be nice to try to make performance counters work on Cobalt 100 and Google Axion, and also test other ARM CPUs and other cloud providers to see how they behave. And Something that could be interesting would be try to use smaller AWS dedicated instances and check if they also have low variation. Because if this is the case, it would be possible to have consistent results with a lower cost. Another possible line of investigation that could be helpful would be to try to detect performance degradation. And we could, for instance, invalidate a run if it was detected that the performance was severely degraded in that run. And also, it would help to do a deeper investigation of the causes of the interference and better understand why they happen and which are the most affected workloads. And yeah, that's it. Thanks. Any questions?
Yeah, hi, over here. Okay. Yep. So, did you manage to figure out why the variability is coming in the instances? Did you manage to pinpoint where this is coming from?
Actually not. I was not able to investigate why. I have some hypotheses, most those one in the first slides about CPU cache pollution or contention in memory access, but no, it would need a deeper analysis to understand why they happen.
Okay, and by any chance, did you compare it with the existing AWS Intel instances? If you have seen the same variability on the Intel instances as well?
Which type of instance?
On the Intel x86 instances.
Oh, no, I tried only with Graviton3 and 4. I haven't done tests with Intel ones.
Okay, sounds good. Thank you.
Thanks for the talk. You mentioned that you reckon that there was no dynamic scaling of the frequency. How did you make sure of that? I thought Gravitons don't allow to fix CPU frequency via CPU frac. Did you ensure that the governor was like performance, that it's always at highest frequency, or did you measure it at runtime?
Yeah, for this was mostly based on the description of the instances and some other tests that were available on other sites that set the CPU frequency, but I didn't run something to make sure that the frequency really didn't suffer any variation during the run.
You could, one can, I used to measure it at runtime, just, write kind of wrapper library that links at runtime and it measures at the background. I mean, it's a bit of an overhead, but you could do that. It's a bit of a pain, but yeah. But does it have? I mean, it has a scaling driver, right? So you can at least access the frequency at the you're reading the node files of CPU frac node files, I believe. It should be possible. I mean, so in principle, you could just check it by hand while it's running, or you could write something that will be measuring it on the go.
Right. I think you are not allowed to change it,
right. But you can access.
But you can read, right?
Okay, good.
Yeah, this would be nice to add in the next run.
But it's nice that they allow PMU readings. So the kernel paranoid setting, you can change it to -1. Is it?
Yes, you can change it.
That's nice.
Since it doesn't expose all of the hardware PMU counters, but they expose some, and there are a lot of events available.
I see. Thank you very much. Thanks.
So the conclusion sounds like the advice of the cloud providers that if you want predictable performance, use a bare metal instance is correct, unless you want to take some risks. But if we say, okay, we're going to do all our spec benchmarking on a bare metal instance, how many of the spec benchmarks can actually saturate that whole instance and get good results? Because I'm imagining, like, what if you have a single core benchmark I've got 95 CPUs doing nothing. I get a great result, but it doesn't feel great because a lot of it's idle.
Right, but your intent would be to run more copies of the same benchmark at the same time, or other instances of SPEC that could be running different benchmarks at that same time?
I'm thinking, could you run other instances, but would that then create interference, which is giving you the same problem? Or are there SPEC benchmarks that need to be run over, say, 96 CPUs to produce valid results? Because, for instance, you could have a cloud provider that this economically is a bad idea, but they might provide bare metal 4-core instances, and that might actually be more suitable for some benchmarking than the large Graviton instances.
Right. Yeah, I haven't tried this scenario, but I suspect that there would be some interference in this case, especially if the benchmarks that you're running were not the same. There could be more, for instance, cache pollution if they are running different benchmarks at a given time. But I haven't tested if it gets much worse or if it's better than having unknown interference from other users.
And taking Amazon's example, 96 cores is just a sort of gut reaction. Is it useful to run some sort of spec benchmark over 96 cores? Is there any use case where you'd actually do that, or is like 10 cores enough for assessing multi-core performance?
Multi-core, I don't know exactly the answer, but I would say that at least 8 cores, but 96 seems a bit too much.
Yeah, so diminishing returns probably, but maybe need another set of graphs to actually prove that. Probably, yeah.
Right. Okay, any other questions? No? Thanks, everyone.